This mini lecture will serve as an introduction to logistic regression, in which we'll talk about the theory behind what logistic regression can do, some of the advantages, some of the assumptions that we make, and some of the data screening processes that we need to go through in order for logistic regression to have a proper interpretation. So the purposes of logistic regression, in other words, the different situations we might use logistic regression, we first need to think about the fact that logistic regression is a form of other regression processes or other regression analyses, including linear regression and multiple linear regression. In linear regression and multiple linear regression, we're typically working with a numerical outcome of some kind. But if we would like to predict a single categorical outcome, like passes or fails an exam, having a disease, not having a disease, possessing a risk factor, not possessing a risk factor, we can use logistic regression to predict that sort of an outcome. We're still able to use multiple numeric and or categorical predictors to make this prediction. So it becomes a little more useful, allows us a little more flexibility compared to what we can do with multiple regression. So we're still going to use several possible variable selection processes. We have our stepwise regression options. We have our enter method, in which we can force all the variables into the model simultaneously. So a lot of those selection processes are not going to be different from what we see in multiple regression. So what this model does, it predicts the probability of a subject or a participant having group membership. So what's the probability that someone will pass an exam based upon the predictor variables? What's the probability they will not pass the exam based upon predictor variables? So some of the advantages behind logistic regression include the fact that there does not need to be a normal distribution of scores for the predictor variables or the independent variables. So when we do correlations, when we do linear regression of either simple or multiple linear regression, one of the assumptions is that the predictor variables, if they're numeric, need to have normal distribution. So we don't need to worry about them being normally distributed. We don't need to worry about them having homogeneity of variance. So this again allows us a little more flexibility in the kinds of predictor variables we may use. Now when we calculate out the probabilities, it will not produce negative prediction probabilities. So again, that makes interpretation a little bit easier. We can have a very definitive idea of what's the likelihood that someone is going to have a certain group membership. And so that makes interpretation and communication of what the model is telling us a little bit easier. So all probability values that are produced when we create the model, and you'll see that more when you watch the YouTube video of the actual analysis steps. The probability values are always going to be positive and are going to range somewhere from 0 to 1. Another advantage is, as I mentioned earlier, we can use independent variables or predictor variables that are in any measurement scale. They can be categorical, they can be ordinal, or they can be numeric in nature. So again, that allows us a lot more flexibility in coming up with different predictor variables to predict the outcome or the group membership. Another useful advantage here, again, which is different from linear regression, is that if the dependent variable has a nonlinear relationship with any of the independent variables, in other words, there's some kind of a curvilinear relationship between the two, then we can use logistic regression. We wouldn't really be able to do linear regression because of that assumption of having a linear relationship between the outcome and the predictors. So when we run into a situation where we have that nonlinear relationship, logistic regression becomes an alternative option for us. And then of course if we want to do a categorical outcome, logistic regression is also an option for us. So some of the assumptions we have to make when using logistic regression, and a lot of these assumptions are kind of the part of the screening process that we go through to look at data and prepare data to do logistic regression. And they tend to be fairly similar to some of the processes we go through with multiple regression. And so there is a lot of crossover between the assumptions and how we determine if we meet the assumptions. So when you do multiple regression, you can use a lot of these techniques I'm going to demonstrate here in a few minutes for multiple regression as well as logistic regression. So one of the first assumptions that we make is that we have a reasonable sample size. And the rule of thumb we typically use, if we can have about 15 subjects per predictor variable, that's considered to be kind of a basic minimum of a sample size. Part of the issue we run into is if we have fairly small samples relative to a large number of predictors, that can really reduce the statistical power of the analysis, and that will make the model be a little less accurate. So if we've got, towards the minimum number of subjects, but we have large numbers of variables, predictors, like 5, 6, 7, 8, 9, 10 different predictors, and we've only got maybe 10 or 12 or maybe even just 15 subjects per predictor, that can significantly reduce the power. Another issue we run into is if we are using predictor variables or independent variables that are categorical in nature, and we possibly have less than 5 cases in one of those categories. So let's say we're saying that someone either lives in a rural setting or lives in an urban setting, and we're using that as a predictor. If I've got less than 5 people that maybe fall into the rural category, that's going to significantly affect how well the model is going to be able to predict. We'll end up having a poor model fit when we have small numbers of cases within a single category of a categorical predictor. When that happens, some of the options we have are to maybe collapse categories into one another, or maybe combine categories, or to eliminate that particular predictor so that we can increase the size of cases within a category. Now the next assumption we can look at, which is one we had talked about when we talked about multiple regression, that's the issue of multicollinearity. And that's where we have intercorrelations between our predictors, between our independent variables. If we have 2 predictor variables that are highly correlated to one another, then that means they're more or less measuring the same thing. And so that creates some redundancy, and these 2 variables may actually suppress each other to a certain extent, so it's difficult to see the true effect of 2 predictors that are measuring the same thing. So how we deal with this is we will check for bivariate correlations between our predictors, and if we can find that there's a bivariate correlation with an R value greater than 0.70, then that would consider to be an intercorrelation, and we might want to consider either combining those variables or eliminating one of them. So that's kind of the first step, and we do that just by performing bivariate correlations among our different predictors. Another option we have is asking SPSS to produce something for us called collinearity diagnostics. And there are 2 common quantitative measures that SPSS will give us to determine collinearity. And I'll demonstrate where you find these in the output when we look at an example here. But one of the first is called the tolerance statistic. And what we basically look for are values less than 0.10. And if we see values less than 0.10 for a given model or a given predictor, then that indicates high collinearity with other predictors. The other value we look at is known as the VIF, or the variable inflation factor. And this will also give us an indication of, the variance inflation factor, and this will also give us some indication of whether or not we have high collinearity. So if the values for this particular measure are greater than 10, then that would indicate that we have some interrelationships and there's high collinearity. And I will demonstrate in a few minutes here how we find those in the output. The last assumption we have to worry about is some are looking for outliers. And we look for outliers in quite a different way than we do when we just have basic quantitative data. And we use something called the standardized residuals, and we also use scatter plots in order to determine these potential outliers. And so we're going to use PP plots. We're going to create PP plots and look for kind of a standard arrangement of the data points and whether or not it meets that arrangement, that assumed arrangement or not. And then we can also use scatter plots, which will give us an idea if we have a particular variable or sets of scores that fall outside of an acceptable range of scores. And we use standardized residuals to, again, determine those. And I'll also talk about how we do that in a few minutes. Another set of variables we look at to determine outliers is something known as the Mahalanobis distances. And we can calculate those in SPSS, and SPSS will give us those values, and we can use that to, again, determine if we have any outliers. So that gives an overview of some of the different advantages, certainly, and some of the assumptions we have with logistic regression. So what I'm going to do next is go ahead and open up an SPSS data file and show you how you can actually ask for these different diagnostics so we can see if we can meet these assumptions, specifically the multicollinearity assumption and the outlier assumption. Now, one drawback to SPSS as far as the logistic regression function, it doesn't allow us to do many of these diagnostics within the logistic regression function. So we actually have to go into the multiple linear regression function in order to do some of these diagnostics. And then once we've done the diagnostics and we've made our decisions whether or not we've met the assumptions, then we will do the actual analysis in the logistic regression function, which you'll be able to observe when you look at the YouTube video. So what we have here is we have a set of data in which we're trying to predict whether or not someone's going to pass or fail a licensing exam. And so we have several measures that are going to help us determine that. We've got GPA, we've got their score on the GRE exam, the quantitative portion, the GRE verbal portion. We have a score on something known as the Miller Analogies test. And then we have a test that's labeled AR, which is a test used to assess critical thinking. So obviously the higher the scores on these particular variables, indicating greater achievement or greater intelligence or better critical thinking. And then we have our categorical outcome, which is either passing or failing the exam. So a 1 represents passing the exam, a 0 represents failing the exam on the first attempt. So what we want to try and figure out is if any of these collections of predictor variables, these first 5 variables here, to see if these will help us predict group membership, in this case passing or failing the exam. So the first thing we need to do is determine if we're meeting the assumptions of logistic regression. So we need to go through some SPSS functions in order to determine that. So we need to go to the Analyze menu, and we're going to go to regression and then linear. Remember, we're just doing this for the diagnostics. When it's time for us to run the actual logistic regression model, we're going to go to the binary logistic function, but we'll get to that after we do our diagnostics. So Analyze, Regression, Linear. All right, so we want to move our outcome variable into the dependent variable box, in this case passing or failing. And we want to move our remaining predictor variables into the independence box. So we want to move each of those variables. Again, we might have more than the 5 that we have here. We might have several, but these are the 5 that we have to work with. So the first thing we want to do is click on the Statistics button, and we basically want to ask for, we can uncheck these, and we want to ask for collinearity diagnostics. All right, and down here in the residual section, we want to ask for case-wise diagnostics. And we want to make sure that outliers outside are checked. And the criteria we use is 3.3 standard deviations. Okay, so that's a typical criteria that we use, that if we have a standardized residual outside 3.3 standard deviations, we consider that to be an outlier. All right, then we click Continue. All right, then we click on the Plots button. Okay, and we're going to click on 2 standardized variables and move them into the X and Y scatter plot. So the first variable is star ZRE SID. and we want to move that variable into the y-axis. And then the next variable is called star ZP, P as in Paul, RED. And we want to move that one into the x-axis. Okay. And then where it says standardized residual plots, we want to click the normal probability plot option. And then we click continue. And then the last thing we go to is we click on the save button. Okay, and then on the section labeled distances, we're going to check the Mahalanobis distance. Now sometimes we can work with Cook's distance as well, but the Mahalanobis distance is probably the most common one we're going to work with. Okay, then we click on OK. And then we click on continue, and then we click on OK. And it's going to give us our output. Okay, there's one factor I forgot to ask for, so my apologies. So there's one more thing we want to ask for before we do our analysis, and that's asking for a correlation matrix that will tell us if there are any intercorrelations among our predictor variables. So let's go back to our Analyze menu, and there's one more box we need to check. So go to Analyze, Regression, Linear, and then under Statistics, make sure we have Covariance Matrix checked, and that will allow us to see if there are any intercorrelations among our variables. So I apologize for that. So click Continue, and then click OK. Okay, and now we can look at our variables here. So the first box we want to be interested in is looking at this coefficients table, and this is going to give us an idea if we have collinearity based upon the tolerance in the VIF measure. So again, if the tolerance measure is less than 0.10, that's going to indicate the fact that there is collinearity. And as we look at each of the variables here, we can see their tolerance values are all greater than 0.10. The other value we can look at is the VIF value, and we had stated before that if this value is greater than 10, then that indicates collinearity. And as you can see, none of these values exceed 10. So that's looking good. That's meaning we're not having any collinearity. The last thing we can look at is here are our predictor variables, and here are bivariate correlations with each of the predictor variables and the other predictor variables. And so what we're looking for are R values that exceed 0.70. As you can see, as we scan these R values, we can see that none of these are greater than 0.70. So it looks like we don't have any collinearity, we don't have any interrelationships among our predictor variables, so that is a good sign. That indicates we're meeting that assumption of no collinearity. All right, the next thing we can do is go down, page down a little bit farther, and now we can look for any potential outliers. And one of the first ways we can look for that is that Mahalanobis distance that we had talked about earlier. And you can see that particular variable is right here in the table down there at the bottom, third from the bottom. And what we do here is we look at the maximum value for this. Okay, and what we need to do then is, using a chi-square statistic, we come up with the critical value for chi-square and the degrees of freedom we use to come up with a chi-square value for p less than 0.05. And for degrees of freedom, we use the number of predictor variables we have minus 1. So in this case, we have 6 predictor variables, independent variables, and that would give us a degrees of freedom of 5. And if we're using the p less than 0.05 value in order to determine if we have an outlier, our critical value then would be 20.52. So if our maximum distance value exceeds 20.52 in this particular case, then that would tell us we have an outlier. But as you can see, our maximum value here is 9, so that does not exceed 20.52. So based upon our evaluation, we would say that it appears we do not have an outlier. and so we're meeting that assumption. Another thing we can look at to determine outliers is the PP plot, and what we expect to see is the majority of the dots kind of following along with this line. And if the dots are clustering around that line, we like to see them all perfectly on that line. But as long as they're clustering close to that line, that will indicate that we do not have any outliers. Okay, so if we have some deviation from that line, that's okay, but we'd like it to see the dots be as close to that line as possible. So in this case, again, this is giving us some confidence that we do not have any outliers. Now the last thing we can look for is the scatter plot. And what we like to see is we typically like to see two lines that are horizontal. So this collection of dots we would like to see be horizontal, and this collection of dots we would like to see be horizontal as well. And so they almost form two parallel lines that are horizontal, and we like to see those two parallel lines clustered around a value of 0. So ideally I'd see a horizontal line of dots somewhere right here, and then I might see another horizontal line of dots somewhere right here. When we have this angular setup like we see here in these two, in this example, that indicates that there might be some scores that are approaching being outliers but are not outliers. And as we look at the values here, we use that 3.3 value as kind of our criteria for outliers. We can see there's a few values that are approaching 2 and a few values that are approaching -2. We use positive or negative as our outliers. We've got a -2 out here, we've got a +2 out here, so we have some values that are approaching possibly being outliers, but they do not. They're not considered to be outliers. Again, positive or minus 3.3 standardized residuals would be the criteria for having some data point be an outlier. Now, if we had a cluster of data points that exceeded that plus or minus 3.3 criteria, then we'd have to be concerned. But if we just perhaps have one data point or maybe two data points approaching that, then that would not be a concern for us. We could probably go ahead and go with the analysis. And again, with smaller data sets, smaller numbers of subjects, if we only had 1 or 2, that could be problematic. If we had 1,000 subjects, having 1 or 2 outliers would not be as problematic. So that's somewhat of an interpretation we have to make. But it appears that in this example we've used here, as we looked for outliers and we looked for multicollinearity, that this data has met the assumption, and then we can feel comfortable moving on to do the full-on logistic regression analysis. So this is hopefully a pretty good primer on the data screening process we have to go through with multiple as well as logistic regression, and gives you a handle on the kinds of diagnostics that we can use. So as you watch the YouTube video on doing the actual logistic regression, the assumption in that video is we had gone through this process that we just reviewed to make sure that the data fit those assumptions.